Okay, welcome everybody to lecture 8 in our series on functional programming. Apparently people seem to like my shirts. Today is my favorite topic. We're starting to talk about monads. So I have a very special shirt today. This is a shirt I designed myself. The shirts, this batch of shirts I bought from a very nice artist that had a little Volkswagen van on the Bridge of the Gods between Oregon and Washington, and she sells these beautiful, beautiful tie-dyes. And one day I went to her and said, could you make one that has all the primary colors, my favorite colors? And then she made this, so this is a very special t-shirt for me for a very special occasion today when we're going to introduce monads. Before we go jump into our lecture, however, I want to point you to some interesting things on the web, some interesting functional programming links. First of all, I want to point you to Richard Bird's homepage. Richard is the master of the functional Perl. A functional Perl is a little paper that explains a beautiful algorithm or beautiful piece of functional programming in a couple of pages. And Richard has been doing that his whole career. So if you go to his homepage, it's amazing. It just goes on and on and on and on and on and on. Let's see how many, nearly 80 beautiful papers, small papers, where he does very nice calculations of functional programs from specifications. So I can really recommend any of these papers. Just pick one, print it out, and enjoy it. Another thing that that we talked about was prime numbers. I forgot exactly in which lecture it was. I think it was lecture 5 or 6, where we had a very naive way of generating prime numbers. Well, prime number generation is another hobby of functional programmers, and I've here 3 papers about that. This one from Colin Runciman about lazy evaluation and generating prime numbers using the prime number wheel. If you read the paper, it will be clear why this is called the wheel algorithm. A paper I can recommend. Then there's an interesting paper here which says this is all the other things are not really the sieve of Eratosthenes. So this is the real one, and as you see here on the screen, I don't know if that's readable, but there already right in the introduction you see some beautiful Haskell code. And then the third example, and there's plenty more, is Lambert Meertens, where is another master of program calculation. Bird and Meertens, even it's called the Bird-Meertens formalism, the kind of style of calculating functional programs. Also, Lambert's papers are a must if you want to become a real functional programming Jedi. And Lambert has written a paper on calculating the sieve. And here I want to do a little plugging myself. In lecture 7, I talked about the various recursion schemes like anamorphisms and hylomorphisms and so on. And here you see a couple of relevant citations right in Lambert's paper. Grant Malcolm, who is really one of the pioneers of having these recursion schemes, and it references here his PhD thesis. I think there's other papers from him that you can get. I mentioned that Graham and Jeremy Gibbons had a paper on the expressive power of faults and so on. They also have a paper on proof methods. How do you prove properties about programs that are written using faults and unfaults and so on. And then my paper there at the bottom, that gives you all these kind of crazy things. This is like, when I was a young Erik, when I was a crazy guy, how can you ever come up with a title like functional programming with bananas, lenses, envelopes and barbed wire? But if you read the paper, it hopefully all makes sense. And then the first two citations here are older papers that really kind of lay the foundation. If you look at the Darlington and Burstall paper, that is one of the early papers that showed how you could derive algorithms by repeatedly unfolding a definition and then folding back another definition. So that is why it's called the kind of unfold-fold system. And then the first one is some early work that Richard Burt did about memoization of recursion. So if you just follow these 5 links here, you can spend weeks enjoying the beautiful foundations of functional programming. Okay. As I said, today's topic is monads. But we will hide them a little bit and we will call them parsers. But whenever you see this, whenever you see parser, that parser is a special case of a monad. So what is a parser? Well, a parser is a program that takes a piece of unstructured data or data that has very little structure, like a string, like the string 2 times 3 plus 4. And as we all know, a string is just a list of characters. So it takes a list and turns it into something that has more structure, in this case a tree, where you want to make explicit that times binds stronger, multiplication binds stronger than addition. So when you type in 2 times 3 plus 4, you really mean 2 times 3 plus 4. And that is obviously clear in the tree on the right hand side, where you add 4 to the result of multiplying 2 and 3. So what we're going to do is we're going to derive or design parsers that can take strings into these structured trees. And I really don't have to explain this to you, but in practice nearly every program does some form of parsing. If you even look at Hux or GHCI, that takes your program that you type in the command line, which is a string, it parses it and then it executes it. If you look at, you see, we should teach Graham. Well, he's okay. He mentions Explorer here. He also mentions Unix, but any operating system, when you write shell scripts, and on Windows that would be of course PowerShell, that also takes a string, parses it into the abstract syntax, analyzes that and executes that. And a web browser takes an HTML document, which is basically an array of bytes or a string, interprets that, parses it and shows that in your browser. Now the last example here is interesting, because if you look at HTML documents, they are very hard to parse using a context-free grammar-based parser, because the XML is often messy. So a parser is not necessarily a parser that is defined in this way. A parser is anything that takes something from one structure into something of another structure. And in that respect, really you can view almost every program that you write as some form of parsing. But let's kind of concentrate here on parsing strings into trees. So let's write down the specification of our parser. Well, it must be a function that takes a string to a tree. That's what we have been saying all the time, so let's write that down. Type parser is a function from string to tree. Now, this is correct, but not convenient. because this definition is not very compositional, because it kind of, you know, only shows us the end result of a parse. We put in a string and out comes a tree. But this definition doesn't allow us to break up. It doesn't show us, it doesn't give us any hint how to break a complicated parser into smaller parsers, because there's no string on this side. So it's like a black box. I put in a string, out comes a tree. But there's no handle for me to kind of peel the layers of the onion where, you know, for which I need another string such that I can apply a parser to that. So how do we get that? Well, we do that by realizing the following. If you parse a string, you get a tree, but usually the string is not completely consumed by the parser. So what we do instead is say, well, what is a parser? It takes a string and returns a tree, and it gives me the remainder of the string that was not consumed by producing that string. So that's the modified definition that you see here. A parser is a string, is a function from string to a pair of a tree and a string. Now let's generalize this a little bit more. And I'll modify the definition here. And you already see the answer on the slide. So this takes a string and a tree. And so this is the unconsumed input and the tree that you produce. Let me be consistent here and put the tree first, not to confuse you. Now what happens if you cannot find a parse? So in that case you don't have a tree. So what do we do? Well, and one way is to say, well, this returns maybe a tree or a string, where type maybe is defined as nothing or just A. So this is the way in Haskell to define an optional value. So an optional value of type A is either nothing or it's really a value of type A. So one way to would say, like, I take a string and out comes maybe a tree and a remainder of a string, where maybe can be nothing if there's no parse and just the result if there is one. This is okay, but Haskell programmers are often lazy, or I don't know if it's really laziness, because if you look at this thing here, what you can also see is that, well, this maybe type is very much like the list type, right? If I have a list of A, well, I can map nothing to the empty list, and I can map just to the singleton list, or A cons empty list. And now I don't need to define a new type maybe. I can just use lists for this, and that now I can use all the functions that are defined on list. The whole standard prelude, map, everything. I could define all of them on the maybe type, but it's much more convenient to reuse list. So you're not as strongly typed as possible, but it's much more convenient to use a list. So typical Haskell, experienced Haskell programmer will use a list here. And that's exactly what we see here. A parser is a string from a function from string to a list of a pair of a tree and a string. Now if you look at, for example, F#, there or in ML, people probably will do much more with a maybe type, or what they call their option. I think it's written in F# and OCaml and ML, like I always forget, something like this. There the types are postfix. So they would use, instead of list, they would use the option type. That's an interesting difference in the culture. Even within the functional programming community, each subculture has very different ways of doing things. But in Haskell, you prefer lists over maybe types because it's often more convenient, especially if you get nested results. If you get list of lists, then having this maybe type in between is not very convenient. So we end up with the following type. A parser is a function from string to lists of pairs of trees and strings. And for simplicity, because that is the easiest thing to do, we will not think about parsers that can return more than one result. So we're really using this as a maybe, and it either succeeds with a singleton list or it fails with an empty list. But if you look at all the papers on parser combinators, they will return multiple results. But it's for this lecture, we stick with the simple one, where you either return the empty list if there's failure, or the singleton list if there's exactly one result. So what we're doing here is we're defining recursive descent parsers in a functional style. Let's define our first parser. And this parser has type parser of character. And what it's supposed to do, it is supposed to look at the input string and return the first character of the input as the result. Okay? And I should go back here because I forgot something really important. Because I didn't say what we did with this tree, because in general, as I said, what do we want to do with this parser? We want to take a string and recognize structure in there. So instead of putting this fixed type tree here, we need to put here A. So what we end up with is parser of A is a function from string, and it returns a list of a pair with the value that we've parsed and the remaining input. And this list is empty if there's no parse, and it contains exactly one element if we found a parse. All right. Now let's look at this function here for item. Item has type parser of characters. So if I apply this definition, funny thing here is that just like how we reason about programs, we reason about types in the same way. I look at this type here and I just expand its definition. So what we want is a function that takes a string and returns a list containing a character and is a pair containing a character and a string. If you expand the parser type like this, again, the type dictates what this function should be. Since we know that strings are a list of characters, so really what this thing is, again, I expand string into list of characters. I have to return a pair of a list of characters and a character. Hey, well, the only way I know how to take a list of characters into a character and a list of character is by taking the head and the tail. And that's exactly what you see in the definition here. So an item takes the input string. If the input string is empty, well, I have to return the empty list because I cannot split down the empty list into a pair of a character and a list. Otherwise, if the list is not empty, I take the first element and the rest of the list, put that in a pair and return that as a singleton list. lesson here is you look at your types, you stare at your types carefully, and there's no other way than defining it like this. The types dictate exactly this definition. So the item parser takes a string and returns a list of a pair of a character and another string. And in this case, in order to find that out, we had to unfold, we had to do some equational reasoning on the type level, just like we do equational reasoning on the expression level in most cases. Here's another trivial parser, the parser that always fails. And that's the Erik parser, right? I always kind of cause accidents and whatever, so it's, I take any input and I return it into failure. So that one is easy to define. And then there's the other one. This is always, everybody knows somebody that is like the return parser, the parser that always succeeds. No matter what input you give it, it will always succeed. So in this case, it takes a value of type A and returns a parser of A. And how does it do that? Well, by just copying the input and returning that value V immediately. Again, these two functions here are completely dictated by their types. Failure and return. This one is a little more interesting because that one is not quite obvious. So let's look at the description. We need to find a operation, triple plus, that takes two parsers that both produce an A and return a parser that produces an A. And this combinator behaves like choice. So what it should do is it should behave like parser P if it succeeds, and it should behave as parser Q if parser P fails. Once you read that text, the definition is pretty obvious. So how do we do that? Well, again, our parsers are defined as a function that takes an input into a list of pairs. We have two parsers. Let's apply the input to the first parser. That can return one of two results. It can fail, in which case it returns the empty list. And the specification said in that case the result should behave like Q. So what do? I return the result of parsing Q on the input. In the other case, the parser returns exactly one value, say V, and the remainder of the input, in which case I just ignore parser Q and return the result of parser P. So that one was straightforward too. And if you've ever written a recursive descent parser in C or in any other language, you will recognize this one too. This is the alternate construction where you're trying to parse one. Only if that fails, you're trying the other one. And then the last one is an interesting function. That's the function parse that takes a parser and turns it into a function that takes a string to a list of pairs of type A and string. Well, fortunately things are here still on the board. That function takes a parser of A and returns a function of string to A and string. Well, but these things were the same. That's how the type parser is defined. So guess what? That is exactly the identity function. Parse of P and input just applies P to the input. It's the identity function. I could strip out, parse of P equals P. I can strip off the input. But it still makes sense to put in that function because, it makes this type conversion explicit. So you often see that people put in functions like this just to make it explicit, even though it's the identity function. And in this case, parse was defined as a type synonym, but if parse was defined as an algebraic data type, this function would most probably strip out the constructor and then apply the function to the input, in which case it wouldn't be really the identity but very close to the identity. And in some sense this parse function is the destructor of the parser type. Good, so we've defined just a couple of simple functions and we can already now write some programs that do that. So let's look at the first example here. Parse item on the empty string. Remember that item, what it did is it would return the first character in the input string. Well, since the input is empty, it's the empty string, it will fail. And that's what you expect. It returns the empty list. If I parse an item from the string ABC, that should return the first element, the first character of that string. And guess what? If you type that in, you get the singleton list of the pair that has the character A and the remainder of the list BC. This style of programming, where you define a couple of functions and then you go to the REPL loop and try it out, this is something that you do a lot in Haskell. And as we said before, F# has the same thing. The F# REPL loop, what you would do is you would scrape and paste these expressions into the REPL loop to see the results. That's a very nice way of developing your code, developing an API to get a feel, a very quick feel, get very quick feedback. You write you define your functions, you type them in, you see how they feel, you check if they work, and then you go back and define more. Let's look at another one. The failure parser. Well, they should be able to give it anything and it should always fail. And failure was indicated by the empty list. So parse of failure of the string ABC returns the empty list. The return parser would leave its list, its input alone and return the value that you specify there. So exactly as you expect, if I say parse return of 1 ABC, I get the singleton list with the result 1 and the input list is just left untouched. Let's look at this one where we're using the choice. Parse either an item or return immediately D. Well, if I apply that to the list ABC, since that's not an empty list, that will succeed. So it will return item of ABC, which is the list A followed by B and C. And if I start parsing and the first alternative is a failure, well, in that case, the choice behaves like a second parser, in which case it immediately returns D and leaves the output unchanged. So just by checking a few little programs here, you can get a good feeling of whether the parsers behave like you expect that they behave. Now, of course, this is not a substitute for careful programming or writing unit tests and so on. One thing that a lot of Haskell programmers do is they use a test generation tool, like a popular one is Quick Check, where you write a specification of your program and then this tool will generate random test cases for you and try to find counterexamples. Quick Check, I can really recommend that. And maybe if we have time in the end, I might, and there's demand, I might do a lecture on that. A couple of remarks. The code for this is available on Graham's website. And there's a couple of things here that have to do with typing. Let's skip over that. The third one is what I want to talk about, is that really what we have shown here is our very first example of a monad. And people often, when they hear the word monad, they get scared. It's like, oh, monads, oh, that I don't know what that means. That's something that has to deal with category theory or something super complicated and theoretical. No, 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 no. A monad is something very simple. It's something like this parser, and it is a process. The way to kind of have some intuition about monads, it's that it's a computation that returns values of type A. And how does this computation work in this case? Well, it's something that takes a string and returns a list with the remainder of the string that contains the value I'm interested in. So here you see all the things that I need in order to compute my value of type A are hidden in this parser type, and that's what a monad typically does. A monad is some type, M of A that represents some complicated computation that delivers a value of type A. And the type of the monad abstracts away from all that computation. In this case, that there's a string and it returns a list and whatever. So as the consumer of type parser, you don't have to know how this parser is implemented. You just glue together the functions that come with this parser library. Only if you implement things like item, you have to know the underlying structure. You have to know what is the process that you use to compute that value of type A. Since these things are monads, you can use monad comprehensions, and in this case it's the do notation. And the do notation requires that you have a function called bind. In Haskell it's defined like this. In C#, this thing is called select many. And that is what makes it possible to write parsers like this. Let's write down this guy. So what we really need is we need to have a function that takes a parser of A, function from A to parser of B, and it returns a parser of B. So Brian Beckman would say, this is composition. Yes, it's more like application. It's like if I have a function from A to parser of B, and I have an argument of type parser of A, this thing here peels off the parser, performs the computation, takes that value of type A, passes it into this function, and out comes a parser of type B. However you interpret this, what you see here is that this is a way to allow you to compose different parsers. So I can take a parser, then I can take a function that depends on the result of that parser, returns a new parser, and then I can combine these two into a result parser. And that's what you see in this notation here, with the do notation. So the first thing says, give me item as a parser, and then we use this generator notation that we know from list comprehensions. I think I have enough space here. So remember from list comprehensions when we wrote x such that x in x's. This was the generator notation where this one had type list of A, and the other side of the arrow had type A. The same in the do notation. When you write do inside the do notation, I like to write curly braces. In this case, you say x drawn from item. In this case, the fact that there's an arrow here, what you see is that this thing has type parser of A, and that guy has type A. So the thing on the right of the arrow is something of type parser of A. The thing on the left is of type parser, and you see here that this really corresponds to this bind, where I have something of type parser of A, and then on the left I have something that expects an A and returns a parser of B. So this do notation kind of boils down to using this bind operator, which in LINQ corresponds to select many, and this do notation here corresponds to LINQ query comprehensions syntax with from select notation. Alright, so let's look at this parser. P is a parser that returns a pair of characters. And how does it do that? Well, it first runs the item parser to get a value called x. Then it runs the item parser again, but is not interested in the result. And then it returns the item parser again, calls that result y, and it returns x plus y. I'm going to make a little bit of space here. What you see on the slide is the following notation, and I will write it using curly braces. So you say, give me x from item. And then I like to write the semicolon here. Then it says parse an item. And then it says, give me y from item. And then it says return x comma y. Now this is an abbreviation for saying, z from item. So if you don't use that value, you don't have to write it here. That's something that we don't have in the LINQ sequence operators. You always have to give a name here. Another way to do this would be use underscore here. And so you can, if you don't use this, you're only doing this to parse the second item, but you're not interested in returning the result. You can write it like this. But I probably would have written it like this and give them names anyway, but I only return the first and the third. But what you see on the slide here is an abbreviation for that. In LINQ, we would write this like this. We would write from x in item, from z in item, from y in item, select new x comma y. So you see that LINQ is just another notation for monads that we have in Haskell. And it would be a nice exercise to define this parser type in C# or VB or F# and see how all the examples that we do here in Haskell's do notation would look in C#'s query comprehensions, or in Visual Basic query comprehensions, or in F#'s computation expressions. What you will recognize is that a monad is any type that implements the standard sequence operators, such as the parser type that we have seen. Okay, so look at this example. Graham depends here on the layout rule. The layout rule in Haskell means that white space in your program is important. So each element there must start on the same column. That's why I prefer to use explicit curlies and semicolons. This is something that people in the University of Utrecht often write, the kind of style where you line up the semicolons like this. The value of this intermediate parser was discarded, so you don't have to do that. And then the value of the last parser here, this when you write return here, remember that return took something of type A to type parser of A. So here you write return explicitly. In the LINQ queries, that is done implicit when you write, the select clause injects this result implicitly. So in Haskell, you can write any function here, and that will be the result. In C#, that is a little bit harder to do. All right. Let's run our parser here. As I said, that parser tries to parse a string, and it tries to parse 3 characters of the string, and it throws away the middle one. So if we apply this P to the string A, B, C, D, E, F, it will return A, C. It has dropped the B, and the remainder of the string is D, E, F. If we try to parse a string that doesn't have at least 3 characters, like A, B, it will return the empty list, and it will fail. Let's look at another parser here. A parser, instead of item, that is kind of, willing to return everything, always returns the first element. We want a parser that takes a predicate and only returns the character if it satisfies that predicate. How do we write that? Well, we write it as follows. You write a parser here, set of P, that tries to parse an item, always succeed. Then if P holds for that item, then you return X, else you fail. So you see here that this one is very similar to the filter function. But you define it using the do notation in terms of your primitive parsers. Now using this set, you see now that we're starting to layer on top of layer of these parsers. We can now define the digit parser that takes a parser, that parses a character that is a digit. So how do you define that? Well, it's set with isDigit, which is a function from character to bool that checks if a character is a digit. Or we can pass in create a parser that checks if there's a specific character by just passing set with the section predicate x equals. So open paren x equals close paren. It's a function from character to bool that checks if its argument is the same as the one I passed in. And here's another interesting one. If I want to apply a parser many times, 0 or more times, what do? Well, I apply it once and I return the empty list, which is the result of applying the parser 0 times. Okay, so I apply it 1 or more times or 0 times. And how do I apply a parser 1 or more times? Well, I define this recursively. So I parse P, call the result V, then recursively call many. That gives me a list of results, and then I just append the result of parsing P to the result of parsing many of P's. So this many and many one, it's a mutually recursive definition of these two parsers. Now I can use this similar parser here to parse a string of characters. And again, you can use the previous definition to write this one. This one is written explicitly using recursion. If I want to recognize a string, what do? Well, if that string is empty, I immediately succeed, and otherwise I just recognize each individual character of that string. So I parse the character, I parse the remainder of the string, and then I return the result. So here you see we're just using recursion, and again we're doing induction over the list. And maybe, if you're adventurous, maybe you can define this one using a fold R, like we've seen in lecture 7. Okay, so here's another parser that consumes a list of 1 or more digits from a string. What is a list? Well, that's something that starts with a square bracket, then there's a digit separated by commas, followed by a close paren. Let's write down the context-free grammar. That would be open paren, digit, followed by comma, digit, star, close paren. So this is the BNF, and you see that this parser is very close to the BNF. Parse an open square bracket, a digit, many commas, followed by a digit, followed by a close paren. And if we try this out, you try to parse that, you will see what happens. Okay, now this is a very, very simple parser. It only parses one result. And if there's an error, it doesn't tell you where the error happened, it just returns the empty string. And again, you can write sophisticated parser libraries that try to do error correction or that tell you at what line position you are. But again, that's all gravy on top of this. Right now, we're just trying to show you how you can build the kind of, the essence of the parser, and all the rest you can layer on top of this. Let's make this now a little bit more real. Let's write a parser, not for lists of digits, but for expressions. So what do we want? We want to make multiplication bind stronger than addition, and we want to have them both associate to the right. So what does that mean? It means that A plus B plus C should be parsed like this, and if this was a star, it should have been parsed like that. Okay, simple arithmetic operations. You go to any compiler construction book and you will see that you can define that these kind of expressions using a grammar like this. And typically there's this layering, so an expression is a term plus an expression, or a term is a factor times a term, or a factor is a digit, or something with parens, and then you go back to expression. Very typical grammar. So what we'll do first is we will left factor this thing. You see here that both things here is like each alternative can start with the same thing. Like an expression can start with a term, a term can start with a factor. So what we're going to do is we're going to separate these out. So instead of that grammar, we write this one. So an expression is a term followed by plus expression or empty, and the term a factor followed by multiplication and a term or empty. And this it's just like a left factoring, a very common operation you do on grammars. And now we can translate that grammar, just like we did before, we can translate this directly into a parser. So let's look at this one. And I'll read the BNF from this to see if what I'm telling you is true. So this guy, expression, is a parser of int. So what does it do? Expression, it parses a term. And then what does it do? Oh, it parses a character plus, nested thing, a plus followed by a expression or empty. Okay, and let's go back. Expression, a term followed by, I didn't put the parens here, but I used that indentation, a plus followed by an expression or the empty expression. So here you see that this is why this often is called a domain-specific language, because instead of writing, eBNF expressions, you can write directly the Haskell program. So it's an embedded domain-specific language for parsers. And remember the previous lecture we had on higher order functions, where we said one of the advantages of higher order functions is that you can write embedded domain-specific languages expressed as higher order functions. This parser type is an excellent example of an embedded domain-specific language. Instead of having a special notation for context-free grammars or EBNF, you just write Haskell code directly. So we can finish this parser by defining terms. Again, what was a term? That was a vector followed by multiplication, followed by a term or empty. And a vector was a digit or an expression in parens. So you see here that the Haskell program is, you squint your eyes a little bit and you see the underlying context-free grammar. Talking about this, you should really look at Gilad Braga's paper on parser combinators in Newspeak. And Gilad makes a good point where he says, you know, yes, it looks kind of like EBNF, but there's still a lot of noise. And in Newspeak, if you look at how he defines parser combinators, they have much less noise. They're very, very, very close to the actual EBNF. So that's also an interesting experiment. Can you remove even more noise than in Haskell? And Newspeak is an interesting language that for parser combinators definitely achieves that. So Gilad's blog, Room 101, is also a very, very interesting read. So I can recommend everybody to have a look at that and definitely compare his parser combinators to the ones that we have here. All right, last thing is let's define an eval function that takes a string and returns an int. And how does it do that? Well, it does that by parsing that string and then returning the value. So what do? We parse the string. If that succeeds, we know that we get a singleton that has a pair of the value and the rest of the string. So what we do is we take the head of the parse, which gives us that value, and then we take the first element, which is of type A. So that's exactly what eval does, again by looking at the type. It's a little bit of a crude definition, because what happens if the parse fails? In that case, parse of the expression returns the empty list. If I try to take the head of the empty list, that will fail. So in that case, eval will just blow up by giving a pattern match failure of and taking the head of the empty list. But if the parse succeeds, you will see that it just works. Okay, so we have already reached the end of this lecture, our first lecture on monads. I hope that you see the deep beauty in this. And to summarize, a monad is really nothing more than a computation of a certain value where you hide all the gory details of that computation behind the monad operators. And one of the monad operators is the bind here that is this type, which in LINQ is called select many. The other operator is return, and then often you have something like choice. The exercises here go dig a little bit deeper into the parsers. For example, it says, can you extend the parsers with subtraction and division? And you can, if you're really adventurous, what you can also try to do is extend this parser with error. So error information. So instead of returning the empty list, you might want to kind of give the position in the input string where the error happened. Really, it's all up to your imagination how far you can push this. And if you get caught by the parsing bug, there's still today new papers being written about parsing that go way beyond this simple recursive descent parsing. So I hope you enjoyed it. Check out Gilad Braga's blog. Check out Newspeak. Read Richard Bird's papers and have fun and see you next time for lecture 9. Thank you very much.